Now with GRE, a GRE tunnel allows encapsulation of packets via a 24-byte header. So there's a little bit of the overhead we were talking about. 20 bytes of that is actually the new IP address header. And that header is going to contain the source and destination IP addresses of the tunnel endpoints. And I'll show you how we configure a tunnel source and destination address on a serial interface when we're building a tunnel. But again, you're going to have another address header, another full 20-byte header that has the source and destination IP addresses of the tunnel endpoints. And the rest of it is a 4-byte GRE header. Well, it's simple enough, right? I mean, not a ton of overhead. Sounds like a pretty good deal. Well, there's a big problem because GRE's drawback is there is no strong encryption scheme. Believe me, it's as weak as it comes, and that's a pretty big drawback in today's world. Now, this giant flaw is corrected by IP security, generally referred to as IPsec. IPsec does offer encryption along with authentication, and that's why you'll see a lot more of IPsec in today's networks than GRE. More about IPsec here in a few minutes. What I want to talk about right now with you are these data encryption technologies. Because for data to be encrypted, it follows that something's got to perform this encryption. Well, one such encryption tool is the Data Encryption Standard, DES. Now, DES was developed in 1976, and just a few things have changed in networking since then, just one or two minor changes. And the main issue with the Data Encryption Standard is that the key that's used is 56 bits. And a key, by the way, it's just a random string of binary digits. But of course, as you would think, the longer the keys, the harder it is to crack. And 30 years ago, that was fine, but it really doesn't meet today's standards. And depending on which documentation you read and what tool you're using to do the cracking, DES keys can be broken in any time frame from a couple of minutes to a couple of hours, maybe 24 hours if you're really taking your time about it, but it won't take you that long. So the next improvement there was triple DES. You can see this acronymed, if you will, as 3DES or TDES, usually with the numeric 3 in there. It's just what it sounds like. The DES encryption procedure is run 3 times with 3 different 56-bit DES keys. So, a little more help there. But the Advanced Encryption Standard, AES, if you have spare time after you get certified, maybe once you're working on a security certification, check out Wikipedia's page on AES. So it's quite fascinating, at least to me. It can run on any Cisco router that has IPsec DES or 3DES capability, and it is quite difficult to break. Now let's talk about that IPsec architecture just a bit. A couple things here I want you to know about, because IPsec, it's really a combination of 3 protocols. We have Authentication Header, AH, which defines a method for authentication and securing data. And we have the Encapsulating Security Payload, ESP, which defines a method for authenticating, securing, and encrypting data. I'm sure you see that one word is in one of those definitions that isn't in the other one, and we'll talk a bit more about that in a moment. We also have the IKE, the Internet Key Exchange, which negotiates the security parameters and authentication keys. Because with GRE, the tunnel is very simple, as we talked about. And the thing is, there's no negotiation of values before the data is actually sent. There's none of that, but there is some of that with IP security. And again, it's the IKE, the Internet Key Exchange, that negotiates those parameters and the authentication keys. Now, I'm not going to really pick on Authentication Header because it offers a secure security, if you will, or solid security. It provides data origin authentication. We like that. It offers optional anti-replay protection. We like that as well. The drawback with Authentication Header is that the authentication it provides for the IP header is not complete. And that's because some of the IP fields can't be correctly predicted by the receiver. These are what we call mutable fields, and they may change during transmission. Now, will successfully protect the IP packet's payload, and that's what we're really interested in. However, though, does not offer data confidentiality. Now, the ESP, the Encapsulating Security Payload, does just that. As you can see from the IPsec packet illustration, there's an ESP header and an ESP trailer surrounding or encapsulating the data. Now, ESP offers us data origin authentication anti-replay protection, and data confidentiality. So, boy, we keep going back to the TCP/UDP argument, right? And this isn't quite that bad because authentication header does bring us some security, but there is that question, well, if one's so great and the other one's okay, why don't we use the great one all the time? Well, you probably already guessed what those problems might be, and one of them is that it's more processor intensive, ESP. It's much more processor intensive than AH. If you don't need data confidentiality, don't pay for it with a hit to your CPU. AH may meet all your requirements. Now, ESP also requires what we call strong cryptography, and not only is it not available everywhere in the world, it's not allowed everywhere in the world. There are certain things Cisco routers can do with encryption where they don't even want these routers in certain parts of the world, and you're not allowed to export them, you're not allowed to move them around, and they've got a huge warning on a lot of their security devices that basically says don't mess around with this. AH has no such requirement. Now, there are a lot more details to an IPsec VPN than you're seeing here, and you're going to see those in your CCNA security studies. We've got stages as the IPsec VPN is built, values that have to be agreed upon, some values that don't have to be agreed upon. I'm not going to hit you with all of those details here because that's way beyond the scope of the exam, but I do want to give you an illustrated look at the overall process of building an IPsec VPN. And something has to trigger the building of the VPN to begin with, because we're not going to take on the overhead of a 24/7 VPN, right? There's no reason to. It's like a bridge from your laptop to the company. Well, there's maintenance in keeping that bridge up, and we're not going to keep it up 24/7 if you're not sending data 24/7. Well, what happens to trigger the building of a VPN is something called interesting traffic. I love that term, as opposed to all the uninteresting traffic we have to deal with. The reason we call it interesting, we can use an ACL to define traffic, and we could say when traffic leaves this laptop and it's destined for this particular network, then build the VPN. That's basically what we're saying, and that's another reason you got to know your ACLs inside and out, is that that's how we define our interesting traffic. Now, the endpoints then enter into a negotiation of certain VPN values, and that includes the encryption and the authentication methods to be used. Because if the two sides just totally disagree on that, we might not get our VPN. And there's an exchange of Diffie-Hellman public keys, followed by the initiator and recipient authenticating each other. There's your key exchange, your DH public keys, and then your authentication info. And then really you're just about done. Let me flip down one here. There we go. The initiator then proposes values for a service association, an SA, and the recipient responds with the parameters it considers acceptable. The initiator confirms receipt of that info, and bada bing, bada boom, we've got our VPN tunnel, our IPsec tunnel. Now, again, I don't anticipate your NA exam going any of that SA stuff. I mean, if it did, I would give you a lot more information on it, but it's not going to be on your exam. But it will be on your CCNA security exam. So my point here really in showing this to you is that with a GRE tunnel, it's pretty much, built, and that's really it. And with an IPsec tunnel, which does bring us a lot more features, there's a lot more behind the scenes stuff going on before we actually have that tunnel built. Now, at that point, the initiator sends encrypted packets across the tunnel, and the recipient decrypts them with the same algorithm used to encrypt them, which is decided upon in the negotiation along with the shared session key. And the key here, no pun intended, I promise, is that once that data exchange is complete, we want the tunnel to be torn down. We don't want the maintenance of a tunnel that's not being used. We don't want the overhead. And we can configure that in a couple different ways. We could say, okay, after this many bytes have gone across the tunnel, you got to tear it down. Or after the tunnel's been up for so long, you got to tear it down, that kind of thing. But the key there is to realize that the tunnel is not, going to be built the second you open the laptop, and it's permanent. Nothing like that at all. It has to be built and has to be triggered by interesting traffic. Now, we talked about GRE there for a little while, the generic routing encapsulation. And with its obvious deficiencies, it really went out of style. It's just like if the key is just sitting there in clear text, it's all clear text, passwords, and there's just no real strong security scheme at all, then we didn't really want to use it. Well, the thing is, though, GRE has made a little bit of a comeback in combination with IPsec because there are things that GRE can do that IPsec can't do. Now, we used to love GRE's multi-protocol capabilities, but that's not important to us in today's networks as it once was. But combined with a lack of strong security features and that was the big problem. GRE was pretty much dead for a while. Now, IPsec is secure, obviously, but it has its drawbacks. Now, multicast traffic generated by dynamic routing protocols, OSPF and EIGRP in particular, of course, cannot be carried by IPsec. To do that, we've got to run a combination of IPsec and GRE, commonly referred to as GRE over IPsec. Now, don't be confused and think that IPsec can't handle any multicast traffic, because it can. As of iOS 12.4.4, IPsec does support multicast traffic but not dynamic routing protocols. So by combining GRE and IPsec, each protocol helps to compensate for the other's limitation. IPsec adds data integrity and confidentiality that GRE obviously doesn't offer, and GRE offers the ability to carry routing protocol traffic, which IPsec does not offer. Now, you can call it either one of these. You can call it GRE over IPsec or IPsec over GRE. The reason we came up with GRE over IPsec to begin with is that GRE encapsulation happens first, and then that encapsulation is encapsulated again by IPsec, because what you have in effect is a tunnel inside a tunnel. You have a GRE tunnel inside an IPsec tunnel. So a little bit of overhead there, but having worked with it, that does work particularly well. And again, that's the only reason you really even hear about GRE anymore, is when it's used in combination with IPsec. Coming up in the next video, I just want to show you a tunnel. I don't want to just talk about this, and we're going to just build a simple tunnel. I'll show you a couple of commands, a couple of verification commands, that kind of thing, and then we'll move on. So I'll see you on the next video.